Hello everyone, today in this video we are going to talk about acceleration due to gravity, and after this video you should be able to define acceleration due to gravity, find the formula for acceleration due to gravity, and you should be able to show the variation of acceleration due to gravity with height and depth. So when an object falls freely due to the gravity, that time whatever acceleration is produced in the body is called acceleration due to gravity. Now we will derive the formula for acceleration due to gravity, and the symbol for acceleration due to gravity is small g. I am considering the earth to be sphere of mass m and radius r, and suppose I am keeping an object of mass small m on the surface of the earth. So we know the weight of the body is equal to the gravitational force on the object due to the earth. Then we can write weight is mg, and we know gravitational force using Newton's universal gravitational law. I can write g capital M small m by distance between them. So distance between their center is the radius of the earth, so this is r square. So this m and this m get cancelled, so we are left with g is equal to gm by r square. In this expression you can see acceleration due to gravity on the surface depends on the mass of the planet. So heavier the planet, more is the acceleration due to gravity. So for Jupiter the acceleration due to gravity is more than that of Earth, and it depends on the radius of the planet. So if you decrease the radius of the planet, the acceleration due to gravity increases, and if you increase the radius without changing the mass, that time acceleration due to gravity decreases. So if you see the final expression of acceleration due to gravity, there is no small m. That means the acceleration due to gravity on the surface of the earth does not depend on the mass of the object. So whether you take a big mass or small mass, they will fall with the same rate. So if you drop a big iron ball or small iron ball, they will reach the ground at the same time if they are dropped from same height, because the acceleration do not depend on the mass of the object. Okay, now next thing which we are going to discuss is weight of a body is more at pole than equator. So as we all know, the shape of the earth is not a perfect sphere. It is flat at the poles. So radius out here is less and radius towards the equator is more. And we all know acceleration due to gravity is inversely proportional to the radius square. So if radius is more, acceleration due to gravity is less. So for equator, acceleration due to gravity is less, and for pole, radius is less, so acceleration due to gravity is more, due to which the weight of the body is more. Now let us prove it mathematically. As we have discussed, radius of pole is less than radius of equator. So when you reciprocate this sign also get reversed, because see, 5 is greater than 2, and if you reciprocate it, you will get 0.2 and 0.5. So 1 by 2 is 0.5. So when you reciprocate two numbers, the sign also reverse. I am multiplying both sides gm and gm. So this gm by rp is acceleration due to gravity at pole, and this is acceleration due to gravity at equator. So you can see for pole we have more acceleration due to gravity, and if you multiply both sides with mass, that time mg is weight. So weight at pole is greater than weight at equator. Now these are some facts about the earth. So radius of pole is 20 km less than the radius of equator, and when you go from equator to pole, the weight is decreased by 0.5%, and weight is maximum at the pole and weight is minimum at the equator, and in between it changes accordingly. Now using the expression of g, we can calculate mass of the earth and the density of the earth. Now first we will find the mass. So we know this is the expression. Now when you take this m this side, you will get m is equal to gr square by g, and on the surface of the earth value of g is 9.8, and we know radius of earth is 6.37 into 10 to the power 6 meter, and value of g is this. Now when you put the values out here, where m is the mass of the earth, then you put the value and it will come as 5.9 into 10 to the power 24 kg, and it is nearly equal to 6 into 10 to the power 24 kg. We know density is mass by volume, so mass is density into volume, and mass is equal to density and volume of sphere is 4 by 3 pi r cube. Now we'll use same concept over here. So g is gm by r square. Now I'll rearrange the formula. Now I'll rearrange the expression taking mass this side. Now I'll put the value of m, that is density into volume, and volume of earth is 4 by 3 pi r cube, and this side we have g r square by g r square, and this r square get cancelled. Next we'll find the rho, so I'll multiply this 3 this side, so it will be 3g, and I'll take this 4 pi r down out here, and g is already there. So if you put the values, value of g is 9.8, and r we already know from here, and g also we know from here. If you put the value, you will get 5497 kg per meter cube. So this is the density of the earth, which we can find using the expression of acceleration due to gravity. Okay, now we will discuss how the value of g changes with height. In this picture I am considering the earth to be sphere of mass m and radius r, and I am considering 2 points, one at the surface, that is A, and one at height h from the surface, that is point B. So we know acceleration due to gravity at point A is given by g is equal to capital G m by r square. So this is the expression for acceleration due to gravity. Now we'll consider point B. So acceleration due to gravity at this point will be given by gh is equal to capital G into m divided by, now distance is more out here, so instead of r we'll use r plus h whole square. So now I'll divide equation 2 by equation 1. So when you divide equation 2 by equation 1, you'll get this gm will get cancelled, so you are left with r square divided by r plus h whole square. So now your gh is equal to g r square by r plus h whole square. So this is the final expression when this height is comparable to this r, and if this h is very small as compared to the radius of the earth, that time we have to modify this formula. So this formula is only when the value of h is comparable to value of the radius of the earth. So let us find the next formula for which h is less. That time I'll use the same formula and I'll take r common from here. So when you take r common, you are left with 1 out here, and here we don't have r, that time we will write r in the denominator. So this will be r square bracket 1 plus h by r whole square. So because of this square, when I take out 1 r, it will become r square. When you multiply this r square back, you will get the same thing. Now this r square and this r square get cancelled, so I am left with 1 plus h by r whole square. So I'll take this to the numerator. So when you take this to the numerator, the power becomes negative. Now I have to simplify this part. So to simplify this part, we use binomial theorem. So it says that when you have 1 plus x to the power minus n, that time you will get 1 plus nx when x is less than 1. So out here you can see height is small and radius of the earth is large, so that means this value is less than 1. So I can use this expression. So instead of 1 plus x to the power minus n, I can write 1 minus nx. So 1 is 1 and minus 2 is the power, so and h by r is the x. So you are left with this, and this is the formula for acceleration due to gravity at some height and when height is less as compared to the radius. So we have two formula for variation of g with height. Now next we'll see how g varies with depth. So I'm considering the earth to be sphere of mass m and radius r, and I'm considering point B, and if I draw another sphere from point B, I'll get a smaller sphere of radius r minus d, and d is the depth of point B from the surface of the earth. So similarly I can write the acceleration due to gravity at point A is g is equal to gm by r square. Now at point B, that is at depth d, the gravitational force at this point will be due to this sphere, not the larger sphere. So sphere, the portion outside the point B will not exert gravitational force on this point B. So only the portion which is inside this sphere will exert gravitational force on this point. So for this I can write acceleration due to gravity at point B is equal to gm dash. So the mass of this sphere is m dash, the inner sphere, by r minus d. So radius is r minus d whole square. So m dash is the mass of inner sphere. So we know density is mass divided by volume. So mass is density into volume. So mass of the actual earth or larger sphere is rho 4 by 3 pi r cube. So this is the volume of the earth, and the mass of the inner sphere of the earth is m dash is equal to rho 4 by 3 pi, and the radius is r minus d whole cube. So out here you can see this is the larger sphere with radius r, and this is the smaller sphere with radius r minus d. So now we will put the value of m from here. So if you put the value of m, this r square and this r square we can cancel, so we are left with 4 pi g r rho by 3. Similarly for gd, so only I have to change the radius, other things will remain same. So it will be 4 by 3 pi g r minus d rho. Rho is the density of the earth. So now when you divide equation 4 by 3, you will get gd by g is equal to this portion divided by this portion. So out here you can see 4 by 3 will get cancelled, pi g will get cancelled, and this rho. So you are left with r minus d by r. So if you take r common from numerator, so from here when you take r, you will left with 1. So and from d we don't have r, so we have to write r in the denominator. So when you take r common from this, you will get this. If you multiply this back, you will get this. So now you can cancel this 2r, and you are left with gd is equal to g 1 minus d by r. So this is the final formula. For depth we have only one formula, but for height we have two formula, one for small height and another for the height which is comparable to the radius of the earth. Now we can say g decreases with height and g also decreases with depth.